start the introduction. Today we're happy to open the theory seminar for this semester. And so we're happy to have Professor Miguel Cazalilla from NTHU to give this opening talk. I'll just call you Miguel, okay. And then Professor Cazalilla to start. Professor Cazalilla received his bachelor's at Bilbao University, well, at Bilbao. It's called the University of the Basque Country. There must be a nice Basque name for that as well. In 1994, he received his PhD in 1999 from San Sebastian. And after that, he spent almost 2 years at Brown University, and then a little bit more than a year at ICTP in Trieste, and returned to Spain with a Gipuzkoa, is that correct pronunciation? Gipuzkoa fellowship back to Spain. And in 2007, he turned as a tenured research faculty, supported by the Spanish Research Council. And during this period, in 2011, he visited National University of Singapore, and for some strange reason, he ended up as professor at NTHU since May. So the title is there, Extrinsic Spin-Hole Effect in Graphene. So Miguel, the floor is yours.
Thank you very much, Professor Prof, for the nice introduction. And actually, now that he has, I took my PhD from the University in the Basque Country, and the Basque name in the acronym is NTHU. Well, now I ended up in so we have something in common, although in different languages. Okay, so let me begin by starting by thanking my collaborators in this work. So it's actually a team that is scattered throughout the globe. Maybe I can move to this side. It's like I can see. Iris Ferreira is in Singapore, but soon moving out. He's a postdoc in the group of Antonio Castronetto. And Tatiana Rappaport is an assistant professor in Rio de Janeiro. And well, this work is actually motivated by discussions with Barbara Silmas, who is an experimentalist in Singapore. And Zidalakumar is one of his students. He's the guy who's done some of the experiments that motivated our research here. So, I don't know if this.
Also, the oriented a little bit better.
Okay.
Spin it.
So, let me begin slowly. So, what is a Spintronics? I guess many people here are familiar with the name, or maybe they have heard about it, but they don't know exactly what it is. Or you already know what it is, in which case you can fall asleep and wake up in a few minutes. I think probably one of the most beautiful definitions of what this field is after is found in this book by Murakami Nagaosa and Shuten-san, published in Science in 2003, where they beautifully summarize in a couple of sentences what would be the dream to be achieved if we could, eventually realize, what they propose here, which is a phenomenon called intrinsic spin-Hall effect. So I will not describe what is, at this point what intrinsic spin-Hall effect. I will first explain what is spin-Hall effect in a few slides. But what they here is essentially summarize what would be dream in this field, which is, enable devices with integrated information processing and storage units operating with low power consumption and performing reversible quantum computation. So definitely it's a very ambitious dream, which probably you can find a picture here on the front page of Scientific American, right? You could imagine your Intel processor now using spin polarized currents instead of just electronic currents, right? So that's what gives the name to the field. Right? It's the merging of the word spin and electronics. But of course, this dream has met several obstacles before even it was formulated in this beautiful way by Murakami, Nagaoka, and Zhang. And one of them is that it is well known experimentally that if you inject a spin current in a metal, typically the spin current is going to remain coherent for a very short time, and it's going to diffuse for a very short distance. So the order of micrometers. Right? So this is sort of a schematic representation of what happens if you inject spin current in a metal, like copper. Now, how do we generate spin currents? Okay. That's another outstanding problem. Right? If you want to make a device, it's not only good that you can, propagate a spin current coherently for long distances. You also want to have ways of generating spin currents. There is a cheap way. And when I say cheap way, I mean cheap from the theory's point of view. If you talk to experimentalists, it's not so cheap. Is to use a ferromagnet. Right? So ferromagnets are metallic systems, are metals that have polarized electrons at the Fermi level. Right? So if you put this ferromagnet in contact with another system that is not, that doesn't have any magnetization, then if you drive a current between the two, and then you manage to make the current go through, you will inject, carriers with definite spin polarization, right? Which is determined by the magnetization of the magnet. Well, that's, as I said, easier said than made. And some years ago, people came with the idea that maybe there should be another way of generating spin currents without relying on magnetic components, magnetic materials. And this is what I'm going to be talking about. Actually, one of the manifestations of this effect, which is called the spin Hall effect. So this effect was predicted more than 40 years ago by two Russian physicists. It's one of the examples that sometimes the Russians tend to say that they discovered everything before anyone else, and this is true. It went completely unnoticed for more than 30 years until Jorge Hertz, who is a physicist working in San Diego, rediscovered the effect. And it's a very simple phenomenon in which you take a material. I will tell you in a minute what kind of material, and you pass a current. So you drive a car with an electric field, constant electric field here, and then because of the material properties, you detect a spin current perpendicular to the direction of the electric field. Okay. So so this has been seen. One of the materials where this happens is gallium arsenide. I'm not going into the details, but when you drive this electric current and generate the spin current perpendicular to it, eventually, if your device is, if your sample is finite, this spin current will lead to an accumulation of spin on the edges of the sample, right, perpendicular to the direction of the electric field. And you can detect this accumulation of spin using the so-called Kerr effect, the optical Kerr effect. And this was actually an experiment where they detected this, which is a sort of indirect evidence for the existence of the spin current. Okay, so what are the mechanisms that give rise to this spin Hall effect? Well, there are essentially two kinds of mechanisms. I already mentioned one in my first slide. It's this intrinsic mechanism that was discussed by Murakami, Nagaoka, and Zhang, and also independently by Sinova and McDonald in the early 2000s. And the idea is that, well, there is essentially a band structure effect. So you have a material which is, you can imagine that has no impurities. It's like theoretically perfect, and this material has, band structure that has, that is split by the spin orbit coupling, which is a relativistic effect. Essentially, is the effect that is caused by the electrons moving in the field of the ions, which if they are very heavy, they sort of cause a very rapid acceleration of the electrons when they pass close to the nucleus, and as a consequence of this rapid acceleration, they sort of can see the electric field of the nucleus as a magnetic field. This is a relativistic effect. If you sort of take a boost of the electric field, you also get a magnetic field. Right? So this effect is present in solids, especially in solids with heavy elements, and it leads to the splitting of the band structure, and it can lead to the generation of a spin current. When you drive a current through the solid, you can generate a spin Hall effect. But what I'm going to be talking about is not the intrinsic Hall effect, but is the so-called extrinsic, which in most systems turns out to be dominant. Right? And this is not caused by the band structure, or if you want the crystalline structure of the material. It's caused by the fact that we introduce intentionally in the crystal certain kinds of impurities, or we do not introduce them intentionally, but they are just there because that's the way materials are manufactured in the lab. I mean, you cannot make them completely impure. Right? So you sometimes get contaminants, and this gives you this effect. And within this extrinsic mechanism, there are two types of mechanisms. One is a sort of mechanism in which you can imagine that the electrons in the form of a wave packet scatter with one of these impurities, which has some spin orbit coupling, induces some spin orbit coupling locally.
Maybe you should just turn it off.
Yeah, I think it's too noisy.
Sit forward. Sorry about that.
Yeah, that's right. And well, because of the potential that is induced by this impurity short range, typically, when the wave packet comes very close to the impurity, the electron undergoes a side jump, as the name indicates, which is caused by the spin orbit interaction, and the sign of the side jump is delta here, which is perpendicular to the direction in which the wave packet is scattering, has to do with it's proportional to the well, I mean it's different for opposite spin orientations, right? So this is something really small, but if it accumulates, it eventually leads to a spin current because it splits the, if you sort of imagine that you have an unpolarized beam scattering off this impurity, eventually it will lead to the divergence of the spin up and spin down parts. Now the mechanism I'm going to be discussing in this talk is another type of mechanism, which is called skew scattering, and it has to do with the asymmetry in the scattering probability, due also to the existence of a spin orbit coupling locally in this impurity. So let me elaborate a little bit more on this. This is actually a well-known phenomenon. It was discovered by Mott very early on in the history of atomic physics, when he realized that when he was studying scattering of electrons with heavy atoms, and he realized that because of the spin orbit coupling, you will have this asymmetry in the elastic scattering of an electron with an atom. So the skew scattering mechanism is just a translation of that atomic physics into the physics of electrons propagated in a solid, right? Essentially, you can think of the same scattering problem for each carriers, and the other thing you have to take care about in a solid, which is different from scattering of electrons in vacuum, is the fact that you have in a metal you have to fill the levels up to the Fermi level, and you have to take into account the statistics. So you cannot scatter into any state because of the Pauli principle. But apart from that, the physics is essentially the same. Now, how you go about computing this? Well, it turns out that if you try to set up like a perturbation theory for this, which in other words, in terms of scattering, means that you want to solve the Lippmann-Springer equation, and this is the impurity potential, which contains a spin orbit part. Right? Then, the fact that this is asymmetric means that if you compute, for instance, the square of the T matrix, right, and you swap the momenta here, you are not going to get the same result. So in a sense, this is sometimes referred to as breaking of microreversibility, which does not mean that you are breaking time reversal, because this spin orbit coupling does not break time reversal symmetry. Okay? It just means that if the scattering for a wave with momentum k ending in a wave with momentum p is not the same as the probability of scattering with the same spin, with momentum that you have swapped. Right? Now, this property, if you do the first-born approximation, is actually not there. So it's not captured by the first-born approximation. And that's a very important feature of this skew scattering mechanism. In order to calculate it, you have to go beyond lowest order born approximation. You have to really take into account, higher orders in your scattering amplitude. And in this, in the work that I'm going to report in what follows, actually we go to all orders. We solve for the T matrix. Okay? And that's a particularly important thing in the case of graphene. So another word that is on my title is the word graphene. So I think, well, since the Nobel Prize, this doesn't need much introduction, but let me spend one slide on it. As you might know, it's one of the thickest materials. It's just one atom thick. Sorry, one atom thin. It's one of the thinnest materials, but it's considered to be a two-dimensional crystal. And if you just worry about the electronic properties, you could also worry about the mechanical properties. It's one of the strongest materials. But we are not going to be talking about mechanical properties in this talk, but not much. If you just worry about electronic properties, as we do, then you have to worry essentially about the physics of the electrons in the so-called pi orbitals, which come from the pz orbitals of the carbon atoms, which are essentially perpendicular to the plane of this two-dimensional crystal. And we can set up a very simple lattice model, tight binding model, to describe the motion of these electrons hopping on this honeycomb lattice, which describes the arrangement of carbon atoms in graphene. Now T is the hopping amplitude, which is about 2.7 electron volts, so that gives us a very sort of high energy scale. And the physics that I'm going to be describing is actually much lower in energy. And for that, it's sufficient to focus on what happens close to the Fermi level. And because of the arrangement of the atoms on this graphene layer, which is just, you have essentially two interpenetrating sublattices made of the same type of atom, then the bands coming from this Hamiltonian touch essentially two independent points at the edges of the hexagonal brilliant zone, which are referred as the K and K prime point. And if I expand the the dispersion of the electrons coming out of diagonalizing this Hamiltonian around these points, what I get is essentially a two-dimensional version of the Weyl equation, of the Dirac or Weyl equation. So that's the low energy description for this system. And that's why it has attracted so much attention in recent years, because in a sense, people have claimed that this is some kind of small lab for testing essentially concepts in relativistic quantum mechanics and quantum field theory. Now the difference is that instead of moving at the speed of light, like for instance if they didn't have mass, neutrinos do, electrons in graphene move at roughly 1/300 the speed of light. That's essentially the order of magnitude of the Fermi velocity in this. Okay, so coming back to spintronics. What can graphene add to spintronics that, for instance, is not known in the case of ordinary metals? Well, the first thing you can realize if you look at graphene is that it's made of a relatively light atom. And because, for light atoms, the spin-orbit coupling is not very strong, right? For light atoms, you don't have very strong relativistic effects even in the atomic spectra. I mean, then you can expect that for graphene, the spin-orbit coupling is actually very weak. And the estimates come actually from, if you assume a perfectly flat system, perfectly two-dimensional flat graphene, then the spin-orbit coupling will come from the admixture of S and P levels in the carbon atom, and also from the admixture of P and D levels, and roughly the order of magnitude coming from this admixture for the spin-orbit coupling is 50 microelectron volts, which is an extremely small energy scale. So, with it's actually quite safe to neglect it. So the splitting in the band structure of graphene due to a spin-orbit coupling can be safely neglected, because typically we do experiments at milli-electron volt, right, or hundreds of milli-electron volt, not at the order of 50, micro-electron volt. So this is an extremely and almost undetectable energy scale. Essentially undetectable. Okay. So for this reason, people have proposed in the past that it should be possible to use graphene as a passive spintronics system, in which you can inject electrons, which are spin polarized, and because they do not feel this spin-orbit coupling, which can be regarded as some magnetic field, which might disorient the spin of these electrons, then they will be able to propagate, these spin currents will be able to propagate coherently. Essentially, electrons in graphene propagate ballistically for long distances. This is known from transport measurements. So the spin currents is expected they will also propagate ballistically for rather long distances. Well, for reasons that they are still not very good understood, very well understood, the spin length, spin diffusion length of electrons in graphene is definitely larger than in many metals. I gave you the figure of 1 micron for the typical figure of merit in many metals. In graphene, it can be 1, or in some experiments, it has been measured to be up to 2 orders of magnitude larger, but it's not dramatically larger. Okay, it's in the best conditions could be 2 orders of magnitude, which is already quite good, and that suggests that graphene could be used as a sort of conductor for spin currents if one could actually understand the origin of this, of what makes, for instance, this experiment different from this experiment, right? So it's a little bit better than some metals, but not terribly better, not 3 orders of order of magnitude. Okay? Now, what I want to discuss in this talk is not how to use graphene or graphene derivatives, right? It's things that you can make using graphene to used to do passive spintronics, to just propagate currents for long distances, spin currents for long distances. What I want to discuss is actually how can you use graphene to engineer the spin Hall effect. In other words, to create spin currents. Okay? So actually the first step in that direction came from a proposal, a theoretical proposal by Charlie Kane and Eugene Mele from Pennsylvania, where they noticed that, well, if you have a perfectly flat graphene, then by symmetry arguments, the spin orbit coupling should be in the sort of continuum description of this graphene sheet, which is given by the Dirac equation. You should have also a term of this form. Now, the problem is that this term is, the magnitude of this term, the coupling here is 50 microelectronvolts. But imagine that as, you know, as kind of a theoretical Gedanken experiment or something like that, you could imagine that you could make this larger. And they asked the question, what would happen? So, well, what would happen is that essentially you would generate a gap, which could be, if it's large enough, would be detectable experimentally, and this would be actually an insulator. But what they argue in this paper is that this would not be a normal insulator. It would be a different kind of insulator. Actually, they did not invent the word topological insulator in this paper. That came later. But this is actually the first example of a system that would exhibit the quantum version of the spin Hall effect. And that means that at the edge of this topological insulator, of this topological phase, this topological insulator, I would have essentially spin polarized currents. Right? So if I drive a current in this system, I would generate a spin current. And this would be protected by time reversals. Well, as I said, this cannot be realized in graphene because the magnitude of this coupling here is very, very small. So there is a gap, but it's probably undetectable. And people had to look for other systems, and indeed, this was found after a proposal by Suchen-Zhang and Bernavik and Hughes. This kind of physics was found in another system, which are these mercury telluride quantum wells, where some of these edge states have been actually measured. Now, following this discovery by Kane and Mele, there have been proposals on how to turn graphene into a quantum spin Hall insulator, into a topological insulator. In other words, how to enhance the type of spin orbit coupling that would open this gap and make graphene sort of topological insulator. And one of the ideas, which can be found in this paper, is to decorate graphene with clusters, with atoms, with atoms of a sufficiently heavy element such that these atoms can induce a spin orbit coupling. So the idea was essentially, imagine that you could cover graphene with a monolayer of other atoms, like for instance indium or thallium, which would then mediate not only sort of the dominant hopping mechanism in the graphene plane between two hardware atoms, which is between nearest neighbors, but other type of hopping, which is for instance between second nearest neighbors, right? Which is from this white dot to this white dot, so it's represented here. But because this is mediated, it has to happen through virtual hopping onto one of the orbitals of this heavy atom, then the electrons of the graphene plane are given the chance to feel the spin Hall effect on this heavy atom. Sorry, this not the spin Hall effect, the spin orbit coupling on this heavy atom, and as a consequence, you can induce effectively a spin orbit coupling on the layer itself, and this is represented here because when the electrons